welcome you all in this lecture of the heat equation. Today I am going to discuss the two-dimensional heat equation and in particular the steady state condition of the heat equation. Two-dimensional heat equation. Del U upon del T equal to K square del T upon del X2 plus del T upon del Y2 is known as two-dimensional heat equation. This is known as two-dimensional heat equation, and in steady state, that means when your temperature does not depend on time, your del U upon del T will be 0. So we have del T upon del X2 plus del T upon del Y2 equal to 0, and this is known as your Laplace equation. So this is known as our Laplace equation. Now let us find out the solution of this Laplace equation. So let U equal to x of x, y of y, that means simply uxy is the solution of this Laplace equation. Now if this is the solution, then it will must satisfy this Laplace equation. So we have del U upon del x equal to x dash y, and del T upon del x2 will be x double dash y, and similarly del T upon del y2 will be x y double dash. So on putting these two values in our Laplace equation, therefore we have x double dash y plus x y double dash equal to 0. So that means x double dash y equal to minus x y double dash, or you can say that x double dash upon x equal to minus y double dash upon y. And let us assume this one as small k. So we have x double dash equal to small kx and y double dash equal to minus ky. So from here we will have x double dash minus kx equal to 0 and y double dash plus ky equal to 0. Now we can have three conditions on k. The first one is when your k is positive. So k is first. When your k is positive, and if k is positive, then we can consider k as lambda square, where lambda is not equal to 0. Now if k is lambda square, then we have x double dash minus lambda square x equal to 0 and y double dash plus lambda square y equal to 0. So from here we have d square minus lambda square x equal to 0, and again from here say d square plus lambda square y equal to 0, where your d is del upon del x and your rounded d is del upon del y. So in this case you can see that from here our auxiliary equation will be m square minus lambda square equal to 0. So that means m equal to plus lambda or minus lambda. So our CF will be, or you can say our solution will be C1 e to power lambda x plus C2 e to power minus lambda x. And from here you can see that our y will be C1 cos lambda y plus C2 sin lambda y. So therefore your solution is, solution in this case is u equal to x into y. From here our x will be e to power say a e to power lambda y plus b e to power minus lambda y, and from here our auxiliary equation will have root plus minus lambda I. So our solution will be C3, say C a b c cos lambda x, so lambda y plus d sin lambda y. So this is our solution in this case. Now let us consider the case 2. Case 2, when your k is negative, that means that is k equal to minus lambda square, where lambda is not equal to 0. Now if k equal to minus lambda square, then here you can see that this will become plus and this will become minus. So here we will have plus sign and here we will have minus sign. So now if here we have plus sign, then the roots of the auxiliary equation will be c1 cos lambda x plus c2 sin lambda x, and if we have minus sign here, then your third root will be, your root of the auxiliary equation will be e to the power lambda y and e to the power minus lambda y. So in this case your solution will be a cos lambda x plus b sin lambda y, sorry, b sin lambda x, then c e to the power lambda y plus d e to the power minus lambda y. So this is our solution in this case when your k is negative. Then case 3 means when your k is 0. Now if your k is 0, then from here our x double dash will be 0 and y double dash will be 0. So after 2-time integration, your x will be c1 x plus c2. So your solution will be c1 x plus c2 and then c3 y plus c4. So this is our solution in this case 3. Now in physical problems, we will have a square plate or rectangular plate in which either 3 boundary conditions are 0 or 2 boundary conditions are 0, and for those problems we will take either solution number 1 or solution number 2 as our solution. So if our 3 or 2 boundary conditions are 0, then we will take, in case when your 3 boundary conditions are 0, then we will take solution, either solution number 1 or solution number 2. That means either we will take this one as our solution or this one as solution. So let us solve a question in which only one boundary condition is non-zero and rest 3 boundary conditions are 0. So this is of type 1 question, type 1 problem, when 3 boundary condition are 0. That means only one boundary condition is non-zero. So question: a square plate is bounded by the lines x equal to 0, y equal to 0, x equal to 20, y equal to 20 with insulated sides. So let us consider a rectangular plate with lines x equal to 0, y equal to 0 and x equal to 20 and y equal to 20. So the top of the upper horizontal edge is given by the temperature of the upper horizontal edge is given by u when your y is 20 and this is your x into 20 minus x, and the temperature for other three edge is 0. So your problem is to find the temperature at any point of the plate. So find temperature at any point of the plate. So we have to find out the temperature at any point of the plate. So solution, here you can see that, say this is your x-axis and that is your y-axis, and we have to find out the temperature at any point, say inside of the rectangle, this square plate. So here you can see that the length of your plate is 20. So now the temperature for the upper horizontal edge is non-zero and that is equal to x into 20 minus x. So this will be your, so the temperature for this side is x into 20 minus x, and here you can see that your y will be 0. So at this point, this is your say origin, and here your x will be 20 and your y will be 0. So this is your point B and this is your point C. So for this edge your y will be 0 and for this edge your temperature is 0, and here again your x is 20 and your temperature is 0, and for this line your x is 0 and for this edge your temperature is again 0. So our boundary conditions are, we have to find out the temperature at some point, and your boundary conditions are ux 0 equal to 0, that means when your y is 0, u 0 y equal to 0, that means when your x is 0, your temperature is 0, and for the third edge when your x is 20, again your temperature is 0. So for the fourth edge our temperature is given as x into 20 minus x. So on taking these three zero boundary conditions, we will try to solve the problem. So let us take solution of the Laplace equation, that means the rectangular plate or square plate is given by solution of the Laplace equation is your uxy equal to, this was your c1 cos lambda x, or you can write it as a cos lambda x plus b sin lambda 1, that means solution of the case 2, and then c e to power lambda y and d e to power minus lambda 1. So this is your solution. Now if this is your solution, then use boundary condition one by one. Let us start with, let when your x is 0, this will be your sin 0. So we will have 0 equal to a cos lambda x. Then here y is fixed, so this will be your c e to power lambda y plus d e to power minus lambda y. So from here this is your non-zero, so we will have a equal to 0. Now let us take boundary condition ux equal to 0 equal to 0. Now if your y is 0, then your u is 0. So from here 0 equal to, now a is already 0, so b sin lambda x, and then we will have c plus d. Now a is already 0, so this term is 0. Now b cannot be 0, otherwise your temperature will be 0, so b cannot be 0. As b is not 0, so from here your c plus d will be 0. Again sin lambda x cannot be 0, otherwise this solution will be 0. So from here we will have d equal to minus c. So on applying the second boundary condition we have d equal to minus c. On applying the first boundary condition we have a equal to 0. Now let us apply the third boundary condition. Let u 20y equal to 0. That means when your x is 20, your y is 0. So when your x is 20, your temperature is 0. So on the left hand side we will have 0. In the right hand side our x is 20. So we will have b sin lambda into 20. That means 20 lambda. Then in the bracket we will have d is minus c. So this will be your c e to power lambda y minus c e to power minus lambda y. Again c cannot be 0 because otherwise this solution will become 0. C will be 0, b will be 0, and your solution will be 0. So this constant b into c cannot be 0. So we will have sin 20 lambda equal to 0. That means this is your sin n pi. So our lambda will be n pi upon 20, where 20 is the length of the your edge of the rectangular plate. So therefore our solution will be, now you can see that our a is 0. So our solution will be a cos lambda x, a is already 0, b sin lambda x, then c e to power lambda y, then d e to power minus lambda y. So if you want to take c common, then this will be your bc, and your general solution is, your most general solution will be uxy equal to, let us take this b into c as some summation dn, then we have sin lambda x. Now this will be your e to the power lambda y minus e to the power minus lambda y, and this will be your 2 times sin hyperbolic lambda y. So if you put the value of lambda, therefore your uxy will be bn sin lambda. Lambda was your n pi upon 20, where 20 is the length of the edge, into this is your 2 times bn. Here you can write it as 2 times bn and sin hyperbolic lambda. Lambda is n pi upon 20. So this is your solution in this case. Now let us apply the fourth boundary condition to get the value of bn. And the fourth boundary condition was, I think when your y is 20, the value of this, the temperature for this edge was x into 20 minus x. So from here we have, so in the left hand side we will have x into 20 minus x, and in the right hand side we have y as 20. So we will have, now this will become your sin hyperbolic y is 20, so sin hyperbolic n pi. So we will have bn into sin hyperbolic n pi and then sin n pi x upon 20. Now in the right hand side you can see that this is your half range sine series. So in case of half range sine series, our solution is, our bn is, so now for bn we have 2 times our coefficients is, now this whole 2 times bn into sin hyperbolic, this one is your bn. We can also write it as bn sin n pi x upon 20, where your bn is 2 times bn sin hyperbolic n pi. So from here your bn will be x into 2 upon L. L is 20, 0 to 20. Fx is x into 20 minus x into sin hyperbolic, so into sin n pi x upon 20 into dx. Okay, so now bn will be 2 times bn sin hyperbolic n pi. So this is your solution, and we will need the solution in the later on case. So this will be your 1 upon 10. Now let us integrate this term. So integrating this term, we will have x into, we can write it as 20x minus x square. Integration of sine will be minus cos into 20 upon n pi. Then we will have minus sine, and differentiation of this term will be your 20 minus 2x, and then integration of cos will be sine n pi x upon 20 into 400 upon n square pi square. Then we will have plus sign, and the differentiation of this term will be minus 2, and the integration of sine will be again cos n pi x upon 20, then into 20 whole cube, 20 upon n pi whole cube, and then the limits from 0 to 20. Now here you can see that for the first term your upper limit will be 0 and lower limit is again 0. If you put x equal to 0, we will get 0. So this term is 0. And for the second term, again if you put your x equal to 20, then we will have sin n pi, and sin n pi is 0. And if you put x equal to 0, then we will have sin 0, that is again 0. So now only this term will give you the values. So we will have minus 2 upon 20 minus 2 upon 10 into 20 whole cube divided by n cube pi cube. Then for the upper limit we will have cos n pi is minus 20 power n minus 1. So this is equal to, say minus 2 upon 10 into 20 whole square, say 400 divided by n cube pi cube. Then we can write it as 1 minus 20 power n. So now this one is, and in the left hand side we have 2 times bn sine hyperbolic n pi. So from here your bn will be, now this 2 and 2 is cancelled, so this will be your again 2, so this will be your 800, so 2 and this will be your 800 divided by n cube pi cube and 1 minus 1 power n. So now this will be your, now if n is odd, then this will be your 2 time, and if n is even, then this will be 1 minus 1, that is 0. So we will have 1600 here. Please note that here this 2 is not included in this bn, because here you can see that your constant was your b into c, and if we include this 2 here, suppose that if we take 2 times bc as constant bn, then in that case this 2 will not come and we will write bn. This is when you write your 2 times bc, that means when earlier I have written b into c as constant bn, and if you write 2 into bc as bn, then we will have just bn sine hyperbolic n pi, and in that case this 2 will not come. So here you can see that now this will become your 4 to the 8 into 1600 into n cube pi cube into 1 minus 1 power n. So including that constant, taking the whole constant 2 into b into c as bn, this will be your answer, and we can write it as 3200 upon n cube pi cube if your n is odd, and in the remaining cases this will be your 0. So thus we can say that our solution is, therefore our solution is uxy equal to summation, the first term was bn, the value of bn is 16 upon, this means 3200 upon n cube pi cube when your n is odd. So we write n equal to odd, and then we have the value of, I think, then we have the term sine hyperbolic n pi, then next term, this was I think our sine hyperbolic n pi upon 20. Let me check our answer. Then our answer was bn into, the value of the bn is sine hyperbolic n pi. Sine hyperbolic n pi will come here, so this will be your sine hyperbolic n pi. So this will be divided by 1 upon sine hyperbolic n pi if your n is odd. So now we will have divided by 1 upon sine hyperbolic n pi. Now this was the value of, we are putting our solution in this general solution, which was your uxy equal to summation bn into sine n pi x upon 20 into sine hyperbolic n pi y upon 20. This was our, the general solution was your bn into sine n pi x upon 20 into sine hyperbolic n pi upon 20. So this is our final solution of the problem.